Well, welcome and thank you for coming. It's nice to see so many people and so many faces I recognize from last talk. I'm August Dunning. We'll talk a little about Mars today and tomorrow. Today it's going to be, if there's a reason to go, we think we might have found something. I think we might have found a new material in this universe that we didn't think could exist, but actually can be mineable. And that's the teaser on it. Now, this is my friend. And he says everything I care about, because he'd rather have questions he can't answer than answers you can't question. And that's why we're here today. So I'm going to give you maybe the only reason to go to Mars, because this mission is vastly more difficult than anything we've attempted to date. And I'll show you why in a second. The background on me, my Mars interest has been long-term. When I first started working at NASA, I was hired by Dr. Richard Snyder. Snyder designed the landing struts for the Viking mission. I also hung out with Admiral Truly, who was the NASA administrator. And these days I hang out with the congressman and do these offshore board meetings. I also hang out at Caltech and invent crazy stuff and have a bunch of friends that question the theories. That's what we do as scientists. We break theories. If they can't break, maybe they're laws. So the first thing we talked about was, okay, is Einstein right? Is relativity theory right? Is the idea that things moving near the speed of light become infinitely dense because of this idea of contraction? And what we've seen is a pretty good answer. This is a Cherenkov effect in nuclear reactors. The glow you see is the electrons leaving the neutrons to turn to protons and so forth in beta events. And the shock waves are giving you the glow, but the point here is the electrons are traveling faster than the light is. It also occurs in thorium reactors. Thorium reactors may be a big thing in the next century. Not yet, but people really like them. So we wrote a paper. We looked at all these theories. Just three. It's me, Tony Sarantidis, and Don Duke. Unfortunately, Don and Tony are dead now, so I'm the last amigo. And what we found was, in the math, we could prove that contraction is incorrect, and that it was an ad hoc hypothesis added in by Fitzgerald and Lorentz to the Michelson and Morley interferometer experiments to explain why he couldn't detect fringe drift in the ether. And I have this paper, and I'm going to do CD copies out at the table for anyone that wants to see this paper. It's about 20 pages long. But we started then able to bring this into what Einstein came up with. And Einstein got into the math and found that these two terms, because he was incorporating the contraction hypothesis, yielded this result. But when you take that contraction out, E equals mc squared is wrong. It's E equals mv squared. And that means infinite velocity for any object, infinite energy in the system. Beautiful. No, should be no name on this. It's not Einstein's or my anything. It's just this is the law of relativity. Now, since it was light, we started looking at collisions of light. And we're trying to explain, well, why did the electron travel faster than the light does? Well, it turns out that light is interlaced electrons and positrons. And that's interesting, because our idea of subatomic matter and subatomic particle physics may be completely wrong. So we decided, okay, what happens when you break things? Well, the stuff falls apart in picoseconds. But if it's stable, it lasts over geologic time. So we thought, okay, there's two assumptions then. One is that there has to be a neutralization of decay activities to arrive at stable structures, and that there has to be an overarching energy structure that's actually the stability of what we call a physical structure. But remember, this is all just energy. Everything in the room is energy. This air is energy. It's all just energy. So we decided, okay, well, how does this occur? Well, the electric vacuum, which is 10 to the 95th plenum of energy, according to Wheeler and Archibald Wheeler and Feynman, creates these infinitesimal particles at almost no mass and almost infinite velocity, and it sure seems a lot like kinetic energy. And they can pool. But the interesting about them, and our theory, is that when they come together and form these three vector neutralizations, so that V1, V2, V3 equals 0, they're rotating. They've changed linear velocity into angular momentum, and they're spinning, and the parts spin exactly the same time they spin around, so there's a synchronicity of rotating parts creating torque, and we see this in galaxies. Let's play. Come on. There it is. You might have seen this on the Observer show, where these galaxies are spinning, but they're not flying apart. There's a torque involved here. So there's this movement towards the center, and this is a natural, we think, a natural occurrence in matter. So we came up with a theory. If these particles pool into these two-dimensional pools, they collide, they split apart, they create the electrons and positrons. The electrons and positrons going to interlace along those boundaries where they've been interrupted to be three-dimensional, forming neutral particles that can then collide with other neutral particles to form the photons, to form the subatomic particles, to form the prequarks and the quarks, and you end up with a galactic nucleon. Okay? Now, well, okay, there's three quarks and a gluon. Well, yeah, that's part of the theory. You have this structural part protected by an energy density part, and there's your gluon and your quarks, right? So when we look at how this works, okay, that's fine, a nice idea. How does it match what we know from the laboratory? Because you have to match what we know, because we know quite a bit. And sure enough, in galactic clouds, when these things start grinding down, and in these ribbons where stars form, you have a lot of temperature and a lot of electrical activity and a lot of things going on, you end up with these tips being ground off, which decreases the masses, which ends up showing you these isotopes of the nucleons, isotopes of the hydrogen atoms. And we've seen this in just recently. We have these galactic clouds in the Orion Nebula that are millions of degrees. And, of course, temperature is a measure of molecular motion, which means they're grinding and they're combining and they're tearing off their electrons and producing light in different frequencies. And when they get to this form, this is an interesting form because you can have these fully saturated phases in this model of electrons and positrons. Okay, fast forward. We believe dwarf stars are a very interesting phenomenon, and Dr. Robitaille will talk tomorrow about that, because I think this may be what we're ultimately going to be finding, pieces of dwarf stars on these planets. Let's look at Mars real quick. Mars is half the size of Earth. You would think this, oh, it's great. It's like the Martians. Just go there, live there, have fun, whatever. It's not. The Earth has a very, very big and profound electromagnetic field, bigger than all the other rocky planets. In fact, it's the only one like it, and it's very much like the gas giants. That's Mars. You're not protected. You're not protected on the way out. You're not protected there, and you're not protected on the way back. And our field is huge compared to these other rocky planets, and that's the problem. 830-day mission, 180 days out, 180 days back, 500 days on the surface so that as you go around and you match orbits to relaunch to get back to Earth, if you're lucky enough, the radiation environment is impossible to survive. We've seen this on the Curiosity. It had its radiation detector on during cruise phase. A huge proton event happened, which would have killed every single living being on that spaceship if it was a manned mission. When you get on the surface, you have these large proton events and large heavy ion events. They wouldn't survive on the surface. During the day, because the atmosphere has something called a solar tide that I'll get into in a second, you have this expansion of the atmosphere on the solar side, reduction in, as you can see in the blue line, reduction in the atmospheric pressure, and much more penetration of solar energetic particles during your work time. And, of course, the problem with that is we've seen this damage genetic in astronauts already. We're breaking up the chromosomes, we're breaking them into fragments, we're shattering them, and so forth and so on. So what we do right now has to understand that this radiation environment has to be addressed. Well, at Caltech, I work with Bill Johnson's group in the Keck building on glassy alloys. Bulk metallic glass is what we call it, and it has some very interesting characteristics. It's 4 or 5 elements mixed together, and they have thermoplastic qualities, so you can actually form them into shapes at a specific temperature, and they reharden when they're out of that temperature. It's like plastics. So we were studying the effects of high-energy particles on aluminum shielding, and we found that they absolutely will not provide anything from very, very high energy and rapidly moving objects. They shatter and have backflash, and they also have spall that comes inside the spaceship. It can damage stuff inside the spaceship, so that doesn't work. So I work with a group, and I'm one of the co-authors of a patent at Caltech where we form these sheets into these three-dimensional shapes, and then we weld the tips together, like you see in the thing. We took them down to up to Ames Research Center with a hypervelocity gun, hit it about 7 kilometers per second, and no backflash, no spall on the inside. There's a vaporization on the outside, but we catch any spall. So we could make layers of this stuff on the outside of spacecraft hulls. That could solve at least a problem with the micrometeoroid and orbital debris problem. All right, so that's cool. That's good. Now, the next rabbit out of my hat is magnetic metallic glass alloys out of iron and cobalt, and boron and phosphorus. And we've got the first unit. We're testing it. And what we want to do is put this alloy in a vacuum in a furnace and hold it under heat and a very strong magnetic field, as you can see in the third frame. When everything aligns, then we take the heat off of it to bring it back to solid again, or back to non-plastic, but keep that magnetic field on there. So you now have a magnetic. Now that's interesting, because then you can start deflecting charged particles from the front of your spacecraft on the way to Mars. But we're really interested in doing this. We want to make these rings with a toroidal field effect so that charged particles, just like a rail gun, just shoot through these things and put them on ion engines. You've got charged ions leaving an ion engine at about 30 kilometers per second, 56 pounds of thrust. You turn them on, you leave them on for months, you get up to velocity, you get out where you're going. They've done it like the DS-1 mission and some of the other things that you use. With this new possibility of reaccelerating charged ions, we can take it in 5 steps up to 560,000 pounds of pressure. That means 3 of those is the same as an F1 engine on a Saturn V. And without huge tanks of fuel to operate that, it's just accelerating the gas in a smaller container. And you get to Mars in 22 days. 2 days of accelerated boost to get to 300,000 miles an hour. And then you turn around in 19 days and you turn it the other direction and shoot the stuff in the other direction, slow it down and come down to the surface on surface rockets. That means the mission's now this: 22 days out, 30 days on the surface, 22 days back, and you could probably survive that mission. 580 days to 70 days. And you have to, because that's the Martian environment. It's completely blasted by the solar wind on the front face. It induces a false induced magnetic field, so there is no geofield around Mars. It does have, as you can see, these whitish areas, these weird crustal magnetism, they call it. That's kind of a cartoon of what they actually look like. That's the Martian environment. If I was going to plan a Mars mission, that's where I'd plan a Mars mission, underneath those domes of magnetic protection. The MAVEN mission has been up there for a while now, and the MAVEN's been flying in and out of the ionosphere and finding out that, yeah, we're getting these sputtering events where these big storms come through and they blow bits of atmosphere off. They blow hydrogen, they blow carbon dioxide, they blow oxygen off. Look on the backside of Mars, though. You'll see that some of that blue stuff is going right back down to the surface. And we saw that on the Viking mission, where in the morning we found snow on the ground. That's because the atmosphere completely condenses at night. Any water vapor in the atmosphere just completely condenses. And it's a dangerous environment. It's like 96% carbon dioxide. That's unbreathable. You have to be in a spacesuit all the time. It's going to be airlock to airlock wherever you go on Mars. All right? We also know it had a lot of water at one point. It's obvious it had a lot of water. We see the evidence of these events of the water leaving Mars. We see streams. We see groundwater. We see dust. And the way this happens is something that actually Dr. Robitaille discussed last time, was the idea of stars being gaseous balls is incorrect. They're actually liquid hydrogen. They go through periods of extremely active periods, and they start cooling down. That's all they do. But during that very active period, huge solar storms are occurring, these lightning bolts of the gods, as Dave Talbot would tell you about. And these things are completely thousands of times stronger than we get here. I mean, the Carrington event in the 1800s was like minus 1900 nanoteslas. And that was enough to light up all the telegraph lines on the planet, and they dropped and started fires in cities and stuff. That's small compared to what the sun probably could make. What if it's minus 25,000, which it was during the Charlemagne event, or minus 50,000 nanoteslas? I mean, the kind of destruction is incredible. And at Mars, with no electromagnetic field, that atmosphere just gets blown off. As it gets blown off, the atmospheric pressure goes down, water just evaporates, ice just evaporates, and here's the big problem on Mars. You have the solar tide on the sunlit side. It expands. On the back, it completely condenses. And there's your zone of possible liquid water on Mars. Mostly it's frozen or in a vapor form, because on the surface of Mars, it's 22 miles up on Earth. So you can't take a spacesuit off. You have the bends. right? And here's how it works. During the day, the air temperature can get up to 40, 50, 60 degrees. The ground temperature, 60, 70 degrees. So the ice melts out, it evaporates up, and gets blown off in the solar wind. Now, on the Phoenix mission, up in the North Pole area, they actually dug into the dirt. They thought they found salts, which was the remnants of an ancient ocean, but it evaporated, which proved that the ice, under such low pressure, just sublimates right to a vapor. Because what happens during the day is solar energy hits the surface, it elevates these things as a vapor, they get lifted up in updrafts into the exosphere, they get hit by high ultraviolet rays, the molecules get busted off, and it gets blown off into space. And we saw this in the Global Observer mission, where in October they had a huge event that blew a huge chunk of moisture off the planet, atmosphere off the planet, and that's when we realized that this is how this happened. No protection, low escape velocity, and the atmosphere just blows right off. So there you go. We've lost the atmospheric pressure. We've lost the ability to have any protective field at the very beginning, so life cannot evolve without protection from the solar wind. On Earth, no problem. But they did find something. During the Mars Global Surveyor mission, they found these very strong magnetic field effects, mostly in the southern hemisphere, about 12 miles below the surface. So we've got a map here that shows where they mostly are, and ESA shows that there's open loop and closed loop, so if you really want to be anywhere, you want to be in those red areas, not the yellow areas. And I'm saying that something hit Mars that's buried on Mars. And this is the source of these magnetic field anomalies. It's not upwelling of crust and former core and so forth. So let's go a little forward here. Let's talk about hydrogen behavior in stars. Because now we have a new model of hydrogen, a new triangular spinning hydrogen that can connect with other hydrogens at these tips. And what we found is that in the sunspots, as Pierre told us last time, you're getting the spectrum of graphite, which is a hexagonal array. Sheets of hexagonal arrays. And that's perfect for this new hydrogen model. Because in these magnetically aligned zones of sunspots, you can have these sheets either up or down because they're all aligned. They're all, if you're aligned in these arrays, all the norths are up, all the souths are down, and that explains your negative and positive sunspots. And when, of course, in magnetic collapse when you get the flares. And you're getting an enormous amount of hydrogen leaving the planet, electrons leaving the planet. We know it's hydrogen because out at Mars we've measured it, and the solar wind is mostly hydrogen, with a little bit of helium thrown in, and in the tail, in the neutral sheet, plasma tail of the sheath, you see the oxygen, the carbon dioxide, and the other stuff you expect at Mars. So in the old models of dwarf stars that Pierre has fixed, I believe, these are supposedly small objects of degenerate matter, and they talk about in these old papers. But they do talk about the temperatures, and they are fairly low in temperature. And that's interesting because these objects are about as low as a candle flame. And they're big. They're almost the size of the sun, but they're like a candle flame. So it's some form of hydrogen, which I think is this isotope 2 form, where you have these saturated faces that can form these structures, which then can form a face-centered cubic crystal of hydrogen and end up with these hydrogen metallic electric solids. That's cool, because that could be a new material we never knew existed in the solar system and never knew it even existed on dwarf stars until Pierre started understanding these stars. And that's cool. That's new. That's insane. So when you have these highly electric dwarf stars that you can't explain in the normal model of gas stars, because they're not degenerate matter, they're not collapsed matter, they're a new form of hydrogen. So my question is, are there mineable deposits of these magnetic materials, electrically condensed hydrogen in the solar system? Let's go for this. If we know these things exist, maybe this is what it is. And so let's take a different view of things. Now, after I worked for NASA, I went to the University of Chicago, and they have the Oriental Institute, and I was fascinated by it because they have the cylinder seals from Samaria that they do these first lithographs in clay and all this cool stuff. But the Egyptian side had me totally fascinated. Inside the ellipse of this, you'll see a staff, a long rod with this kind of pointy head on it with some other things, the Jed and the Ankh next to it. And that's called cham. Now, that's a star metal. So I have this idea that maybe the evolution of the magnetic crustal areas on the Martian surface are really a star metal impact. One of the things I did see that no one has seen yet is the king Khufu. Khufu, as opposed to only 3 of the pharaohs before him, didn't use the solar disk. He used the black disk. Okay? After Khufu, almost all the pharaohs used the solar disk again. During the reign of Khufu, he closed the temples, he closed the solar worship and all that stuff because something appeared in the sky they weren't expecting, a black object, some new thing. Pharaohs named themselves after stars. Is that what Khufu's saying? That was interesting. But the basic thing with Cham is you only see it with the gods. The god Horus, the god Anubis, the god Osiris, and the pharaohs that ascend to heaven as Osiris after death. And R.K.G. Temple brilliantly went over this stuff in his book, The Sirius Mystery, where Cham, if you really want to evaluate what it is, it's a dense star metal from Sirius. And it's 3 times the weight of gold in the hieroglyphic record. Now, what's interesting is you can see in this, now, this is a really good one, as you can see, you got a red disc on top of Horus. You have the Cham scepter with the pharaoh. You also have all this stuff, the ascender, immortality foods given from heaven. You got the Ankh of everlasting, the Jed of eternal strength, and of course the Cham scepters again. And you only see this on these gods and pharaohs. Is that red disk a red dwarf star? When you look at what the Egyptian religion says, it says that Isis and Nephthys begat Horus, the god of 2 horizons, the Zerahuti, they call him. And he's the god of 2 horizons because he's the god of Sirius and the god of the earth. And he came and created the earth. Now, what's interesting is in visible light, Sirius A is very, very bright. But in ultraviolet, Sirius B, the invisible dwarf companion, is very, very bright. There's a lot of electrical energy coming out of that dwarf star. Now, what's really even more interesting is that that's a depiction of their basic cosmological theory. It's also the theory of the Dogon in Mali, which is a descendant of the Egyptian religion system. But what they know is something that in 1951, French archaeologists went down there, and they knew that this Sirius star was a dwarf star with a 49.49-year orbital period, 7 years of 7 kings, right? And it turns out that we didn't know it was back then. It wasn't until 1975 we photographically proved that it was a dwarf star, a binary system. And they said a 3rd star was thrown off of that system. Here's a friend of mine, Zacharias Sitchin. You've kind of heard of him, the Anunnaki and Nibiru and Marduk. And in the Unimai Elish, the creation tale in Samaria, Marduk comes in, destroys a planet between Jupiter and Mars to create the Earth and the asteroids. So when you put these 3 together, something that tells me, just this is what I'm thinking now, is that something was thrown off from Sirius, came into the system, and luckily, extremely luckily, hit a planet that created our planet. Now, we've seen this in the universe already. We've seen stars come together and be cast off in different directions. We've seen people prophesize that you'll have these planets around these stars moving out of as rogue stars moving out of the solar system. And we've also seen TMR1C in Sagittarius, where there's a 3rd star thrown off of a trinary system. So let's think about it this way. Back when the proto-sun system had a super-Earth between Mars and Jupiter, and we see these kind of planets in all these planetary surveys we've come up with, and I think in the news 3 or 4 days ago, Ben brought up a paper that said, look, we're not finding any of these planets that are really our size at our distance. It's unusual, actually. We're not seeing that gap. There's a gap in that planetary size at that distance. But during that time period, there was a lot of ice out there, because that's how these early planetary systems, organize. All the heavy rocky stuff is at the center, pulling in and pulling it into the sun, and you have these gaseous things making all the water stuff. So here's the idea. Let's see if I can get this. So we had this object come into the solar system, and it had these moons around it, or planets around it. Those planets, according to the Sumerians, hit Mars first, or hit Earth first, and smacked it up. Second time around, because it was capturing the sun, it actually collided with the Earth, or this proto-Earth. During that collision effect, an enormous amount of energy was released, and there was an enormous amount of debris created, which would account for the asteroid belt. But the interesting thing about those kind of occurrences is there's going to be a liquefaction with that kind of kinetic energy. And the liquefaction event could be part of the star. and what was left of what would be Earth. Now, it's very interesting because that creates a mixed debris field that would fan out towards the sun from the impact, and it would create all these comets from all the ice and all this stuff from this proto-Earth and all this debris and this mixed debris field, and Mars, in its orbit, would run right into it. Bam, 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 bam. Okay? There's your planetary star metal impact theory. And now we have Mars with these odd magnetic regions that you can't explain. Now they try to say, well, these are upwellings of core material. Well, okay, where's the gravity and where's the magnetism in the same place? Because you're going to have density, you should have that, and the magnetic areas aren't even near where the heavy volcanoes are, over here in the Tharsis region, or Alba Patera. No magnetic stuff up there. You have these big basins, like Hellas and Argyre, where these impacts that occurred after this happened demagnetize those areas, right? And we've seen this on Earth, too. About 90 million years ago, a large boloid hit Yucatan Peninsula, the Chicxulub event. And sure enough, doesn't affect the gravity much there, but this might have been one of those objects, because suddenly there's a magnetic anomaly there. So, star metal on Mars. Here's the theory. This thing came in, smacked the planet up, our planet, debris field, and that's the stuff that's underneath the surface on Mars. It's only in some area. It's only like a certain degree of it. It wasn't that it just kept happening over geologic time. It's like it happened and it didn't happen anymore. And these are big, big fields. At 200 kilometers, they're really strong. And they're in the southern hemisphere, and they're not even looking at these places as landing sites. I think they should. One of the best ones, the strongest one on the planet, is over by Copernicus crater in the southern hemisphere. That's where they should look for a landing site to study this phenomena. Because if you're going to put astronauts up there, you better have some kind of magnetic protection field over where they're living and operating. We also see this on Earth. The SWARM mission has identified large impacts of what appears to be penetrator magnetics on Earth. And there's maps of that. The difference is, though, the ones on Mars are like an order of magnitudes higher than the ones on Earth. The Moon was also out there during all this. So are there mining possibilities on the Moon? Well, I asked a friend of mine about that. He and I rewrote a proposal for a space station back in '93 that got accepted and actually was the first 3 flights. And I said, well, you were up there, because you've been up there. Did you ever see anything really cool, anything really unusual? This was back when I was still over there in like 1992 or 3 when we were playing around. And it suddenly made sense to me now. He said, yeah, Rainier Gamma, near Rainier Crater. It's this really weird-looking thing on the surface. Topographically, nothing there. Photographically, this wispy thing that just arcs across the surface. Well, the Clementine mission went up there, and sure enough, they found a big magnetic anomaly in that area, right next to Rainier Crater, right underneath that anomaly. When you do the gravitational maps, you see that it's there. There's a closed-loop magnetic material about 10, 12 miles under the surface that has the same characteristics on Mars, where it's looping out and looping back. I don't think that's what it is. Come on, let's be serious. But I certainly think it's worth looking at. And I certainly think that if we go to Mars, we should be going into the southern hemisphere where these magnetic fields are. So there may be a time, maybe 50, 60 years from now, and I'll talk about this tomorrow morning, where we're on Mars. We're mining the metals off of Mars because we found them there. So I believe what you think about you creates. Who knows what I've just done. But yeah, maybe deep 12 miles down, there will be these huge star metal extraction facilities. But let's not go where no man has gone before. Let's go where man has gone before. Let's go to the Moon first, right? So many people would agree the idea is crazy. What you have to determine is that it's crazy enough to be correct. Now, mankind for thousands and thousands of years explored and explored and explored and explored. It's our duty, right? And we've always done this. We're out there to explore the frontier. Thank you.